Hello students, the next topic under module 3 in PSA 2 it is optimal unit commitment. In case of electric power system, the load on the system will generally be higher during the daytime and early evening. That time industrial loads are high as well as lights are on, and lower during the late evening and early morning when most of the population is asleep. In addition, the use of power supply has weekly cycle, the load being lower over weekend days than weekdays. So it is evident it is not economical to run all the units available all the time. So to determine the units of the plant that should operate for particular load, it is a problem of the unit commitment. This problem is very important in case of hydel generation as well as thermal generation. This problem is easily solved using priority ordering and dynamic programming method. The priority ordering, which is a straightforward approach, using this the problem can be solved easily. Okay, here most efficient units loaded first, followed by less efficient units. That is to try out all the combination. We'll see procedure how it goes. First efficient unit is loaded first and checks whether this can supply the demand or not. If it cannot supply the demand, then add the next efficient unit and check whether both can supply the demand or not. Okay, so it continues as it is. Okay, finally the unit most efficient unit plus most efficient unit 2 plus so on least efficient unit. Okay, so divide the load optimally among the units. The exact coordination equation is used. Okay, exact coordination equation not only decides the optimal load division but also it gives the minimum cost, but savings cannot be obtained using exact coordination equation, so we have to go for dynamic programming method. The advantage of this method is it is economical. Though it's economical, the disadvantage is it's highly time consuming. Okay, let us go through the dynamic programming method. The main advantage of dynamic programming method, there is no need to solve the exact coordination equation to get the minimum cost. And second advantage is unit combination to be tried are reduced in number. And here some assumptions are made. The first assumption is for total number of available units, their individual characteristic and load cycle are known priorly. Okay, and second assumption, load on each unit changes in uniform steps of size delta megawatt. Okay, here it follows the priority ordering, but in level 1, okay, most efficient unit followed by next efficient unit. Okay, next the program has to be run, okay, so that a cost curve can be obtained. In level 2, these two units, unit 1 plus most efficient unit 2 plus next efficient unit 3 loaded. Okay, and here the program is run, okay, and cost curve is obtained. So on nth level, in nth level, most priority unit 1 and most priority unit 2, okay, and followed by least priority unit, okay, loaded. Okay, here program to be run, okay, and cost curve need to be obtained. Let fn of x be least cost function, and it is defined the minimum cost in rupees per hour of generating x megawatt by n unit is called least cost function. Let fn of y be cost of generating y megawatt by nth unit, and let fn minus 1 x minus y be minimum cost of generating x minus y megawatt, okay, by remaining n minus 1 unit, okay, by n minus 1 unit. The recursive algorithm is used to compute minimum cost here. So the recursive algorithm goes like this: fn of x is equal to minimum of fn of y plus fn minus 1 x minus y. In this process, the total minimum operating cost and load shared by each unit of optimal combination are automatically determined for each load level. So, no need to use the exact coordination equation to find out minimum operating cost as well as optimal load shared between the unit. Know that input fuel cost, which is AI plus BI PGI plus CI PGI square. So cost of generating Y megawatt by nth unit, which is Fn of Y, okay, which is given by the same formula. The unit is rupees per hour. The next topic under module 3, which is reliability consideration. See, as industries are increasing, okay, and in agricultural field the demand of the electricity increasing, okay, and the day by day household comforts are increasing, okay, so it needs the more power supply, okay, there is increase in demand, okay, so there should be continuity of the power supply. Not only continuity, it should have quality. The frequency and voltage should be maintained properly. So not only we need economical power supply, but also the reliable power supply, okay. So reliable power supply means what? Even though there is a disturbance or contingency or failure or forced outage in the system, there should be continuous power supply with the quality. In order to maintain the continuous power supply even under failure condition, okay, we need a reserve, okay, which is called static reserve or spinning reserve or operating reserve, okay, or operating reserve. The spinning reserve means what? Okay, we need to have reserve. Reserve must be allocated in the units, okay, that is operating. In that initially the demand is 10 megawatt, okay, so there is a 10 megawatt power supply, I mean generator generates 10 megawatt power supply. Occasionally the demand gets increased by 2 megawatt, okay, based on past history, okay, it is decided that there is an increase in 2 megawatt demand occasionally, so there should be extra 2 megawatt, okay. The generator should be designed in such a way that it has to generate extra 2 megawatt whenever there is a need, okay. This is called what? Spinning reserve, okay. So it is defined, it is extra generating capacity that is available by increasing the power output of the generator that are already connected to the power system. How do we increase the power output of the generator? By increasing the turbine power, torque of the turbine. When we increase the torque of the turbine, okay, the input energy gets increased. When input mechanical energy increased, output electrical energy will be increased. To determine the system spinning reserve at any time, okay, Patton's analytical approach is used. Patton's analytical approach. So in order to use Patton's analytical approach, okay, we need to find minimum uptime or failure time and repair time. Okay, so let us consider random unit performance. Okay, the unit will be having operating time as well as unit will be having maintenance time or repair time, right? So if you observe each cycle here, okay, if you observe each cycle here, each cycle will be having minimum operating time and minimum repair time, right? Repair time. So here this is called zero state or down state, this is called up state or one state 1. Okay, here the operating time, which is also called up time, which is indicated by T1 up. Okay, and failure time, okay, which is indicated by T1 down, which is also called down time. Okay, so followed by T2 up, T2 down, T3 up, T3 down. Okay, this is a cycle 3. Cycle 1, cycle 2, cycle 3. So we need to follow the Patton's analytical approach. In order to go through Patton's analytical approach, we need certain data like mean time failure. Okay, for initially we have to find the mean time to failure. Okay, mean time to failure, which is also called mean uptime. Okay, mean uptime, which is indicated by T up, okay, which is the ratio, it is the ratio of summation of uptime to the number of cycles. Okay, similarly, mean time to repair or mean downtime, which is the ratio of, which is indicated by T down, which is the ratio of summation downtime to the number of cycles. Okay, so after finding these two, mean cycle time need to be calculated. Mean cycle time, which is T up plus T down. Okay, here T up is what? Mean uptime, and T down is mean downtime. The inverse of uptime, mean uptime, which is called failure rate. Okay, the inverse of uptime, which is called mean uptime, which is called failure rate. The unit is failures per year. Similarly, the inverse of mean downtime, which is 1 divided by T down, okay, which is called repair time, repair rate. Okay, the unit is repairs per year. Okay, which is indicated by mu, and this is indicated by lambda. This is failure rate, this is repair rate. Here random unit performance is drawn based on the previous data or history. So repair rate as well as failure rate, okay, repair rate as well as failure rates will be calculated based on the past data. Now let us calculate the probability of unit being up and probability of unit being down. Okay, the probability of unit being up, which is the ratio of, okay, which is the ratio of mean uptime to the mean cycle. Okay, mean cycle time which is the sum of mean uptime plus downtime, correct? Sum of mean uptime and downtime. Okay, but we know that T up which is equal to 1 divided by lambda, and T down which is equal to 1 divided by mu. 1 divided by lambda plus 1 divided by mu. Okay, this is failure rate and this is repair rate. Okay, so multiplied with 1 divided by lambda plus 1 divided by mu. Okay, when we multiply it with the 1 divided by lambda on the numerator and lambda on the denominator cancels, it becomes 1 plus lambda divided by mu. Okay, here there is a 1, so multiply and divide it by mu. Okay, and here lambda divided by mu is there. Take 1 divided by mu outside. Okay, because 1 divided by mu here it's there and 1 divided by mu here is there. So take 1 divided by mu outside. So it becomes mu plus lambda inside. Okay, so 1 divided by mu on the denominator, when it goes to numerator it becomes mu. Okay, so finally P up, okay, the probability of being unit up, okay, is mu plus lambda, that is failure rate. It is a ratio of repair rate to the sum of repair rate plus failure rate. Okay. Similarly, the probability of unit being down, T down, is equal to the ratio of mean downtime to the mean cycle time. Okay, that is T down divided by T up plus T down. Okay, so from this, when we calculate P down by substituting the failure rate as well as repair rate, we get lambda by lambda plus mu. Okay, so P down is equal to lambda by lambda plus mu. Okay, adding the probability of unit being up and unit being down, we get P up plus P down is equal to 1. Okay, let this be equation 1, let this be equation 2. What? The probability of being up state means what? The available time or operating. Okay, probability of unit being operating. Okay, probability of unit being down means what? Okay, probability of unit being not operating. Okay, so probability of unit being up is also called probability of unit being operating, which is called availability. I mean probability of unit being available. Okay, probability of unit being unavailable or probability of unit being not operating. The probability of unit being in state I, okay, considering k units are operating, Pi is equal to pi, okay, pi Pj up, okay, probability of unit being up into pi Pl down, Pl down. Okay, so here L, pi varies from 1 to k, okay, and j varies from 1 to k. Here j belongs to y and L belongs to xi. Okay, what is this xi and yi? Xi is units in down state, yi is unit in up state. Xi is unit in down state, yi is unit in up state. We know that summation of xi, where I varies from 1 to n, means what? We have to add x1 plus x2 plus so on xn, correct? So instead of summation, if we have pi xi, I is equal to 1 to n, then what it means? x1 into x2 so on into xn, okay? Take it as equation 3. Next concept is pattern security function. There will be system security in the power system. What it does, it keeps operating the power system though there is a failure. Okay, if there is a failure in system security, then we need to be careful. Okay, pattern security function, it decides the failure in the system security, okay, failure in the system security or breach of the system security. By knowing this, the spinning reserve can be decided. Pattern security function, which is the quantitative estimate of the system insecurity, okay, which is indicated by S, okay, that is quantitative estimate of the system insecurity. S is equal to summation pi ri, where pi is probability of system being in state I, okay, that is pi, and ri is probability that system state I causes failure of the system security. Okay, if there is a failure, ri is equal to 1, okay, if there is a power system security failure, ri is equal to 1, or else ri is equal to 0. Take it as equation 4.